So, good evening and welcome back to this live problem solving session for the NPTEL course Geology and Soil Mechanics. So, in the last class, we started solving a few problems regarding shear strength of soil. Okay, so in this session as well, we'll continue that part with some more additional aspects of the specific content. So as you know that in this week we we have proceeded further and we have learned about this vein shear test, which is a very important test for in situ undrained determination of in situ undrained shear strength of very soft to medium cohesive soils. Uh, Next, we have learned the sensitivity and thixotropy of clay, and finally we have uh, ended up with this Skempton pore pressure parameter. So, considering or based on these topics, we'll be solving a few numerical problems in this session. Apart from this, we couldn't solve one numerical problem in the last session, so we'll start this session with that problem. Okay, so this is the problem which we left in the last session as a homework. So we'll see how we can solve this problem. So this is regarding the stress path, and this question is taken from GATE examination 2020. So the total stress path corresponding to different loading conditions for a soil specimen under isotropically consolidated stress state O are shown below. So these are the stress paths, obviously in terms of total stress. So this is OR, this is OS, another stress path, this is another stress path OQ, this is another OP. Okay. Now this stress path is plotted in Q versus P plot. Okay, that will see what is Q and what is P, and this is the state of stress of the sample, soil sample. So sigma 3, this is the confining pressure or the minor principal stress, and sigma 1, this is the vertical pressure, vertical stress, axial stress, or the major principal stress. Now what we have to basically do in this problem, so these stress paths are basically represent some loading conditions, like four different loading conditions are stated in this problem. So starting from compression loading, then compression unloading, extension loading, then extension unloading, then extension loading. Now we have to find out the correct match between the stress paths and the listed loading conditions. So this is the target, or this is the objective of this problem. Okay, so see, we'll first start with the basic definition of stress path and we'll move further. Okay, so if you can remember, in the last class we ended our discussion with the definition of stress path. Okay, so we'll again reiterate here. Now what is stress path? Stress path, this is a line. Stress path, this is a line that connects a series of points, and each of this point represents the state of stress state of stress experienced by the soil experienced by the soil due to the progress of the test. Now, if we conduct some test and as the test progresses, so the soil sample will basically experience a change in its state of stress, and that change of stress, if we basically try to plot in a very convenient manner, that kind of representation will be called as stress path. So stress path is nothing but a line that will connect a series of points. Now each of these points will represent the state of stress experienced by the soil due to the progress of the test. Okay, so this is the physical significance of stress path. Now two type of representation are in common use. So one is basically one has been popularized by MIT and another one by Cambridge University. Okay, now this MIT one, so both basically use the same notation to represent the state of stress, Q and P, if we talk about in terms of total stress. Now what is Q? So in case of MIT, the Q and P, these are nothing but the top coordinate of the top point of a Mohr circle. As you know that the state of stress can be represented by Mohr circle as well. So suppose this is the top point. So this is your sigma 1 plus sigma 3 by 2. This is your sigma 3. This is sigma 1. And this is nothing but sigma 1 minus sigma 3. Now this sigma 1 minus sigma 3 by 2, this is the ordinate, that is Q, and this is P, that is the abscissa. So this Q and P, so this type of representation, it has been popularized by MIT. Okay, now as you can see from the problem definition, it's something different. So here Q equals to sigma 1 minus sigma 3 and P equals to sigma 1 plus 2 sigma 3 by 3. So as I stated earlier, so this is the second convention or second kind of representation that has been popularized by Cambridge. So here Q represents the deviatoric stress, and P represents the mean stress. Now, as you know that for a triaxial sample, suppose this is the cylindrical sample, so it will be subjected to an all-round pressure, confining pressure sigma 3 and axial pressure sigma 1. Now all-round confining pressure means, so the lateral stresses are same, sigma 3 only. So therefore the mean stress would be sigma 3 plus sigma 3, sigma 1 plus sigma 3 plus sigma 3 divided by 3. So that means sigma 1 plus 2 sigma 3 by 3. So in this way also you will be getting one stress, lateral stress, confining stress. And what is Q? Q, this is the deviatoric stress, and we have been already familiar with this term, that is nothing but sigma 1 minus sigma 3, which is basically applied in the shearing phase of a shear test. So the first one is consolidation phase and next one is a shearing phase. So in shearing phase, so the confining pressure is kept constant and the axial stress is being increased until the soil sample fails. Now this difference between the uh, means the difference which is basically required for the failure of the sample, that is termed as deviatoric stress, that is sigma 1 minus sigma 3. Okay, so please keep in mind that only for this kind of state of stress where the confining pressure is same throughout the soil sample, so for that only this sigma 1 and this will be this deviatoric stress sigma 1 minus sigma 3, since this is a triaxial type of state of stress. However, for true triaxial state of stress, where means in this case the minor principal stress and the intermediate principal stress are same, sigma 2 equals to sigma 3. However, in the case of polyaxial test or true triaxial, your sigma 1, sigma 2 and sigma 3 all will be different. So in that case we will not, this expression will not be valid for the deviatoric stress. Okay, though that is not the part of our study, at least for this course. So we'll only uh, discuss, or will be concentrating on this term sigma 1 minus sigma 3 as the deviatoric stress for a triaxial kind of state of stress. Okay, now based on these two stresses Q and P, we'll be trying to find out the stress path for each of these loading conditions which are listed here. So starting from compression loading to extension loading. Okay, so first we'll start with, okay, and before that please keep in mind that all the samples, all the soil specimens are basically isotropically consolidated. So up to this point O, so this is basically represents the isotropic consolidation. Now what is isotropic consolidation? Isotropic consolidation means consolidation under same all round pressure. So your sigma 1, sigma 2 and sigma 3 all are equal. So your P would be simply sigma 1 plus, suppose this will be simply sigma 3, and your Q will be 0. Okay, so this kind of state of stress we will have at the end of isotropic consolidation. So this represent by point O. So here your sigma 1 and sigma 3 are equal, and again for triaxial test sigma 2 or sigma 2 and sigma 3 are equal. Okay, so P would be sigma 3 or sigma 1. You can represent any one of these two terms. Okay, now we'll first start with this compression loading. So now what are the conditions prescribed for this kind of loading condition? Your sigma 1 is increasing and sigma 3 is constant. Now we can mathematically write that delta sigma 1, this is your not equals to 0, whereas delta sigma 3 is, okay, so delta sigma 1 is increasing and sigma 3 remains constant. So delta sigma 3 is 0 and delta sigma 1 not equals to 0. So this is the mathematical representation of the given loading condition. Now initial condition, as I mentioned, that sigma 1 and sigma 3 are equal. So sigma 1 and sigma 3 are equal, and that is same for all the loading conditions. Okay, so beginning of the loading condition, so this is the initial condition. So therefore your P0 is sigma 1 plus 2 sigma 3 by 2, and your Q0 is 0. Now what will be the final condition? So final condition, so if we try to figure out, so it will be sigma 1 plus delta sigma 1 plus 2 sigma 3 plus delta sigma 3 divided by, okay, so this is divided by 3, and your QA, this would be sigma 1 plus delta sigma 1 minus sigma 3 plus delta sigma 3. Now this delta sigma 3 is 0 because there is no change in the confining pressure. So therefore you can write PF as sigma 1 plus 2 sigma 3 by 3 plus delta sigma 1 by 3. Okay, and QA sigma 1 minus sigma 3 delta sigma 1. So P0 plus delta sigma 1 by 3 QA Q0 plus delta sigma 1. So this is the state of stress what we have basically got from this type of loading condition. Now if we try to plot so this is your Q, this is your P, this is your P0 and Q0. Okay, so again here your Q0 is 0, so therefore you can simply write it as delta sigma 1. Now your stress path will be like this because this is your Q0 and P0. This is your P0 and Q0, and it will basically increase, okay, because delta sigma 1 by 3. So this is the increment in the P, and this is the increment in Q. So this will be the stress path. Now what will be the slope of the stress path? The slope would be, so delta sigma 1, so these are the increment, okay. So this will be, so if you try to plot delta Q by delta P, so it will be delta sigma 1 by delta sigma 1 by 3, that is 3. Okay, so this is the slope delta Q by delta P. that you will get for compression loading. Now coming to, but this slope is not concerned for this problem because the pattern is the major concern for this problem. So therefore we'll coming to the next condition, next loading condition. Next loading condition is your compression unloading. Okay, so at the same time we'll try to make an analogy between the stress path what we have got from our analysis and the stress path which stress paths which are already given in the problem. So as you can see, this OR is better represent this OR better represents the stress path for compression loading. Okay, so this is your O and this is your R. Okay, now we'll be moving to the next case, that is compression unloading. So case number 2, that is compression unloading. Now what is happening in compression unloading? Your sigma 1 is constant and sigma 3 is decreasing. Okay, so it's not only not equals to 0, it's also greater than 0. Okay, so in this case your delta sigma 1 is 0 and delta sigma 3 is less than 0. Okay, so sigma 1 is constant and sigma 3 is decreasing. Now the initial condition remains same in this case as well. So this is your P0 and Q0. Okay, so P0 is your sigma 1 plus 2 sigma 3 by 3 and Q0 is 0. Now what will be PF? So if we calculate first PF, so PF will be sigma 1 plus your delta sigma 1 is not here. So delta sigma 1 is 0. So delta sigma 1 will not write. Okay, let me write it first. Plus 2 sigma 3, then your delta sigma minus delta sigma 3. It's basically reducing, decreasing divided by 3. And Q0, this will be sigma 1 plus delta sigma 1 minus sigma 3 minus delta sigma 3. So as you can see that this value will 0, will be 0, this value will be 0. So here this will be simply sigma 1 plus sigma 3 by 3 minus 2/3 delta sigma 3. Q0 sigma 1 minus sigma 3 plus delta sigma 3. PF would be P0 minus 2/3 delta sigma 3. And okay, so this is not Q0, this is QA. QA Q0 plus delta sigma 3. So as we can see, as we can realize or witness from these two expressions, that your mean stress will basically will be decreasing, whereas the deviated stress will be increasing. So if we try to plot this stress path, so in this QP plot, This is your Q, this is your P, and this is the initial condition. Okay. So now it will basically move in this direction, and obviously with a different gradient. Okay, different gradient as compared to the previous case. Okay, so that we will not determine, though we can easily determine delta Q by delta P by dividing delta sigma 3 by minus delta 2/3 delta sigma 3. Okay, so now as you can see, it's basically matching which line? So this is matching with line OS. So this is your OS. So in this way, we have determined the stress path for compression unloading. Okay. So now we'll consider the third case, that is extension unloading. Okay. And now in extension unloading, your sigma 1 is now decreasing and sigma 3 is constant. So case 3 is extension unloading. That means your sigma 1, delta sigma 1 is less than 0 and delta sigma 3 is 0. So therefore, P0 is sigma 1 plus 2 sigma 3 by 3, Q0 is 0. Okay. So okay, so you can write it, the sigma 1 plus 2 sigma 3 by 3 as sigma 3 also. Okay, so this is sigma 3. If you substitute the value of sigma 1 as sigma 3. Now coming to the final condition, so it will be sigma 1 minus delta sigma 1 plus 2 sigma 3 plus delta sigma 3 by 3, and QF sigma 1 minus delta sigma 1 plus sigma 3. Oh, sorry, not plus, it's minus. So PF would be sigma 1 plus 2 sigma 3 by 3 minus, and here this delta sigma 3 is 0, delta sigma 3 is 0, so minus delta sigma 1 by 3 UF is sigma 1 minus sigma 3 minus delta sigma UF is P0 minus delta sigma 1 by 3 F0 minus delta sigma 1 by 3 minus delta sigma 1. Okay, so here also it's this is 0. So this is the expressions for PF and QF. So as you can see that PF is basically decreasing by minus delta sigma 1 by 3 and QF also decreasing, so minus delta sigma 1. So if we try to plot the stress path for this loading condition, so it starts from so it's basically start from O, and both will be decreasing, your Q and P. So this will be the frame for stress path. So this is the stress path, this will be. Now if we compare this one with the given one, so it will be OQ. Okay, OQ, here you. Now the remaining one is so it's quite obvious, the remaining one would be your OP. However, we'll still try to check. So it is extension loading. So it's extension loading. That is your sigma 1 is constant and delta sigma 3 is greater than 0. Okay, so sigma 3 is your increasing. So sigma 1 is constant and sigma 3 is increasing. So therefore your P0 will be sigma 3, P0 will be 0, and here this will be sigma 1 plus delta sigma 1 plus 2 sigma 3 plus delta sigma 3 by 3, and QF, this is sigma 1 plus delta sigma 1 minus sigma 3 delta sigma 3. Okay, so delta sigma 1 is 0, here delta sigma 1 is 0, this will be sigma 1 plus 2 sigma 3 by 3 plus 2 by delta sigma 3, QF will be sigma 1 minus sigma 3 minus delta sigma 3. Okay, so this will be P0 plus 2 by delta sigma 3 and QF, so Q0 minus delta sigma 3, that is minus delta sigma 3. So if we try to plot, so QF will be decreasing whereas PF will be increasing. So this is P, this is Q, this should be the stress path. This should be O, Q0, P0, and this will be OP. Okay, so therefore we can write your case 1 is matching with OR, loading case 2 is matching with OS, loading case 3 is matching with OQ, and loading case 4 is matching with OP. Okay, let me check it once. So compression loading, it's matching with OR, that's good. Then compression unloading, it's matching with OS, yes. And then extension unloading matching with OQ, and then obviously extension loading OP. So this is the loading condition. And this is the stress path. Okay, so this is the answer. Now we'll try to our next problem. Now in this problem, the results shown in table below were obtained at failure in a series of triaxial tests on specimens of a saturated clay, initially 38 mm in diameter by 76 mm long. Now determine the values of the shear strength parameters with respect to total stress and effective stresses. So that means you have to determine the undrained shear strength parameters and the drained shear strength parameters. Now, in the last class, we basically solved a similar type of problem, but in that case, only 2 test data were given. However, in this problem, as we can see, that 3 tests are performed and the data corresponding to these 3 tests are given. So analytically, it will be quite difficult. So analytically, though we can solve. So in the last session, we solved the problem. We solved the problem analytically. However, in this case, we'll try to solve the problem graphically. Okay. So we'll see how we can determine the shear strength parameters with respect to total stress and effective stress conditions by the graphical procedure. So we'll start with this undrained type of test and then we'll move on to the drained type of test. Now, before proceeding further, let me discuss a little bit about the procedure. So what we'll basically try to do, we need the major principal stress and the minor principal stress. Okay, so this is in terms of total stress condition, and in terms of effective, so it will be sigma 1 prime and sigma 3 prime. And as you know that for undrained case, these two will be different, sigma 1 and sigma 1 prime and sigma 3 and sigma 3 prime. However, in the case of drained test, so these values will be equal. So there is no difference between the total and effective stress conditions. Why? because in case of drain condition, the drainage valve is open throughout the test and there is no chance of generation of excess water pressure inside the soil sample. So therefore, our target is to determine or is to calculate the major and minor principal stresses from the given data, and then we'll try to plot the corresponding Mohr circle. So for this three test data, so this is your tau, this is your sigma axis. So for each type of test, we'll try to plot the data. And suppose plot the data in the sense we'll try to draw Mohr circle for each of this data set. Okay, so one sigma and sigma 3 are known, so you can easily plot the corresponding Mohr circle in the shear stress versus normal stress plot. So you will be getting three such Mohr circles for three data, three tests. Okay, now in the next step we'll try to draw a tangential line, a common line which is basically tangent to all three Mohr circles. So suppose this is the line, and obviously this line should be linear. Okay, so this is the line which is basically tangent to all these Mohr circles. Now inclination of these lines with the horizontal, that will give you the internal friction angle of internal friction, and the intercept along this y-axis at origin, that will give you the cohesion, because this is nothing but the yield envelope sigma c plus sigma. Okay, so this is the philosophy behind determining the shear strength parameters following the graphical procedure or graphical approach. Okay, so in this way, if you can have more than three test data, means, and for this problem we are having data obtained from three tests. Now in some cases you can have more than three test data. Okay, so in that case also you have to basically follow the same approach, that is, you have to first draw the Mohr circles and then you have to plot or draw a line which will be tangent to all these circles. Okay, and from the inclination, horizontal inclination of that line, and the intercept, y-axis intercept at origin, you can determine the shear strength parameters of the soil which you have tested in the laboratory. Okay, so therefore we'll proceed to determine the sigma 1 and sigma 3 from the given test data. And to determine this sigma 1 and sigma 3, you have to keep in mind that this all round pressure, this is nothing but your sigma 3. Okay, obviously in terms of total stress. And what is this axial load? This axial load A, this will give you, sorry, so this will give you the major principal stress sigma 1, that we'll see how we can get the major principal stress from this axial load. This axial deformation epsilon A and this volume change epsilon B, so this will basically this is not epsilon V, this is your delta V, and this is your delta L. So this will try to determine the modified or the corrected area that is required to calculate the deviated stress or the axial stress. Okay, so how that we'll see. So first of all, we'll try to determine the initial area and initial volume of the sample. As you can see, the length of the sample is 76 mm. the diameter of the sample is 38 mm. So therefore, initial cross section is your pi by 4 d0 square, pi by 4 into 38 square, so that is 1134.11 millimeter square. And what is V0? The initial volume. This is pi by 4 d0 square into L0. Pi by 4 38 square into 76. So this is your 86.19 into 10 to the power 3 millimeter. Now, as the test progresses, so the area will be different. So area will also undergo some modification. And corrected area you can calculate from this expression A0 1 minus epsilon b divided by 1 minus epsilon. Okay, and epsilon b is nothing but delta v by v0, and epsilon a is delta a by v0. Okay, how we have got? I think in the last session we have derived this expression for the unconsolidated undrained test, and it was a0 by 1 minus epsilon a, because epsilon v is 0 for undrained test. So this term will be here. Okay, so in the generalized case, so 1 minus epsilon v. So therefore our, and once we know the what we can see say that AC, so we can calculate the deviatoric stress simply dividing the axial load by the corrected area. Okay, so this is the axial load and this is the corrected area. So you know the deviatoric stress, and deviatoric stress can also be represented in this fashion. Therefore, major principal stress would be sigma 3 delta sigma. Okay, so this is for the total stress. So sigma 3 is nothing but the all down pressure, and sigma 1 you can get by adding the deviatoric stress to the all down pressure. Now these values are in terms of total stress. Now to get in terms of effective stress, your sigma 1 prime would be sigma 1 minus u, and sigma 3 prime would be sigma 3. So it will be better to calculate all this data in a tabular fashion. Okay, so we'll first start with undrained scenario. Sigma 3 in kPa, then delta L in millimeter, epsilon A in millimeter, epsilon B, okay, then modified or corrected area F axial load Newton, so delta sigma d kPa, we can get sigma. Okay, let me shorten this table. Otherwise, we'll miss two important entities. So we'll start with epsilon directly. Epsilon v is c a delta sigma d. Okay, if this is, I think, given, not required. Okay, then sigma 1 prime and sigma 3 prime. Both are in. Okay. So we'll first consider the case of undrained. So 200, 400 and 600. So for 200, what is the axial deformation? The axial deformation is 9.83 and the initial length is 76. So therefore, your 9.83 by 76 suppose this is a sample calculation. So undrained case we are now considering, and sigma 3 is your 200. Now what is the delta L value? The delta L value is 9.83 and delta V obviously 0 because this is an undrained case. This is 9.83 and delta V is 0. So we'll first calculate the axial strain and the volumetric strain. So axial strain would be delta L upon L0, so 9.83 divided by, okay, so this is in millimeter. So 9.83 divided by 76, so it will be 0.12 and epsilon v delta v by 0 is 0. Okay. Now coming to the corrected area, this will be A0 1 minus epsilon v divided by 1 minus 11 34.11 minus 0 divided by 1 minus 0. So this is approximately 1302 millimeter square. Okay. Now we'll calculate the gravitic stress. Your axial load is 222 Newton. So get delta sigma T as F by AC. So F 222 divided by 1302. Okay, so this will be 10 to the power 6 in Newton per meter square. 10 to the power 3 in Newton per kilonewton per meter square. So this is 170.5. So sigma 1 would be sigma 3 plus delta sigma T 200 plus 175. So 370.5. Now your U equals to 0. Sigma 1 prime, sigma 1 prime, and sigma 1 and sigma 2 prime equals to 6. So if we follow the same calculations for other two confining pressures as well, so we can fill this table in this form. So it's 0.129. The AC is 1302. This is 170.5. This is 370.5. This is not required. Okay. Okay, sorry. This U will not be 0. But this is not required because we'll determine this undrained shear strength parameters only, not the drained. Okay, so from the undrained case, we'll only determine the undrained shear strength parameters. So if we need to determine the drained shear strength parameters from the undrained test data, then we need to consider the pore pressure data as well. But here in this problem, the pore pressure data is not given. Okay. So 0.132, 0.135. So these are the axial deformations for 400 and 600 kPa confining pressure respectively. Therefore, the corrected area would become 1307 and 1311. The deviated stress is 164.5 and 172.4. Therefore, the major principal stress becomes 564.5 and 772. So this is for the undrained case. Now coming to the drained case, the same calculation we have to follow. Okay, so again the confining pressures are 200, 400, 600. The axial deformations are axial strain 0.142, 0.161 and 0.186. So in this case the volumetric strain will not be 0, 0.077, 0.095 and 0.110. So we have obtained this volumetric strain by dividing the change in volume by the original volume. Okay, del V upon V0. Now this AC be 12220, 1220, 1223. Delta sigma T will be 338.3, 693.4, 10. Okay, so in this way we have got the sigma 1 and sigma 3. Now for the drained case, your sigma 1 and sigma 1. Now with this value sigma 1 and sigma 3, we will draw the Mohr circle. So as you can see, these are the Mohr circle. So this small Mohr circle, so this is suppose your 1, this is your, okay, this Mohr circle 1, this 2, and this is 3. Okay, sorry. Okay, so this 1, 2, 3, this 1, 2, 3 Mohr circle are drawn by considering this undrained test data, that is 200. This is the sigma 1 370.5, 400, sigma 1 is 564.5, sigma 3 600, sigma 1 is 772.4. So for example, Mohr circle 1, 200 and 370.5. Okay, so this is your 200, the minor principal stress, and this is the approximately 370.5. So this is the major principal stress. Now after drawing these 3 Mohr circles, so this line, which is basically tangential to all 3 Mohr circles, are drawn. And as you can see, this line is having 0 inclination, so your pi u value is 0, and this is the undrained cohesion Cu. And what is the value of this undrained cohesion? So this is approximately 85. Okay. Similarly, coming to the drained case, so this is your Mohr circle 1, this is your Mohr circle 2, and this is your Mohr circle 3. Now a common tangent all these Mohr circles is drawn, and cohesion intercept here is 0, so that means your C prime value is 0. However, the horizontal inclination, that is phi prime, is noted to be 27 degrees. So therefore, the shear strength parameters we can summarize in terms of total stress. Your undrained friction angle is 0 and undrained cohesion is 85. and effective stress. Your drained friction angle is 27 degree, but drained position is 0. So these are the answer. Okay. So one request to all of you. So I did this calculation already. So therefore, your task is to cross check all these values because I might be wrong in the calculation part. Okay. However, the philosophy behind determining the system parameters, it's the same. It remains the same. Okay. So in this way, you can also determine the system parameters of a given soil sample under means in terms of total and effective stress by following the graphical approach. Okay. So you have to just draw the mode circles and then you have to make or draw a common tangent to all these mode circles. And before that, to draw the mode circle, you need to know two stresses, the major and minor principal stresses. Minor principal stresses is usually the confining stress. However, the major principal stress you have to calculate from the given data in this fashion. First, you have to calculate the axial strain, then volumetric strain, then the corrected area, and then the deviatoric stress. And that deviatoric stress you have to add with the confining pressure to get the major principal stress. Okay. Okay. So if this is fine, then we can take our next problem. So in this problem, the following results refer to a consolidated underrain axial test on a saturated clay specimen under an all-down pressure of 300 kN per meter square. Draw the total and effective stress paths and plot the variation of the pole pressure coefficient A during the test. Okay. So at the beginning of this session, we have solved one problem that was regarding the stress path, but in that case the stress path was already given to us and we have to match the correct loading condition with the correct stress path. However, in this problem, the test condition is referred to as consolidated underrain and the data are given and we have to construct the stress path both in terms of total and effective stresses. Okay. So therefore, unlike the previous problem, in this case, we'll follow the representation stress path representation used by this MIT one. Okay. So that means your Q equals to sigma 1 minus sigma 3 by 2. So this is in terms of total stress, and in terms of effective stress, it will be sigma 1 minus sigma 3 prime by 2, and sigma 1 prime is nothing but sigma 1 minus u, sigma 3 prime sigma 3 minus u divided by 2, and that means sigma 1 minus sigma 3 by 2. That means Q is equals to, that means you can write your Q and Q prime both are equal. Now coming to P, so this is your sigma 1 plus sigma 3 by 2. Okay, so this is nothing but the coordinate of the top of the mode circle. So this is the abscissa and this is the origin. So P prime would be sigma 1 prime. Okay, one more thing. So the sigma 1 plus sigma 3 by 2, that can be written as sigma 1 minus sigma 3 by 2 plus sigma 3. Okay, so that means Q plus sigma 3. So P prime, this we can write sigma 1 prime plus sigma 3 prime by 2. It is sigma 1 prime by sigma 3 prime by 2 plus sigma 3 prime. That is Q prime Okay, will not write in this fashion, rather write sigma 1 minus c is e minus c. So these are the important expressions which we have derived, that is q equals to q prime equals to sigma 1 minus sigma 3 by 2 p q plus sigma 3 and p prime e minus. Okay, now why we have derived this expression? Because if you observe the given data carefully, the Davidic stress sigma 1 minus sigma 3 is given and the pore water pressure. And in addition to that, the delta L by L0, that is the axial deformation, the axial strain is given. So first we'll calculate the Q and Q prime by dividing this Davidic stress by 2, dividing the Davidic stress by 2. Now once this Q or Q prime is obtained, so we can calculate the mean, not mean, sigma 1 plus sigma 3 by 2, that is P, as Q plus sigma 3, means adding the confining pressure to Q, and P prime by subtracting the pore water pressure from the P value. Okay, so here your sigma 3 prime, the all down pressure is 300 kilonewton per meter. Okay, now this data q prime p prime, these are required for plotting the stress path in terms of total and effective stresses. However, to draw or plot the variation of pore pressure coefficient A during the test, as you know that your pore pressure parameter B is delta Q3 by delta sigma 3, and that is 1 for saturated soil. Okay, not exactly 1, close to 1. And AB, the product of parameter A and B, so this is now if this B is 1, so then we can represent as delta U1 by delta sigma 1 minus delta sigma 3. Now for consolidated undrained test, this delta U1 you can write a simple U value, and this is sigma 1. Okay, now with these expressions we can make a table. So table in this form. So first delta L by L0, this is 0, 0 0.01, 0 0.02, 0.04, 0.08. Okay, next sigma 1 minus sigma 2. So this is your 0, 138, 240, 312, 368, and 410. And then your pore pressure U, so this is your 0, 108, 158, 178, 182. So these are the given data. Now we'll try to calculate the Q and Q prime value, because both are equal, and this will be simply sigma 1 minus sigma 3 by 2. Okay, so that means this will be 0, then 138.2. This is a sample calculation, so 69. This is a sample calculation. Then 240 by 2, 120, 312 by 2, 156, 368 by 2, 184, and 410 by 2, 205. Then P. So this is Q plus sigma 3. So that means 0 plus 300. That is 300. Okay. So then 69 plus 300, that is 369. 300 plus 120, 420. 300 plus 156, 456. 300 plus 184, 484. 300 plus 205, 505. Now coming to P prime, this is your P minus U, minus 0, that is 300. Okay, 369 minus 108, that is 261. Okay, 420 minus 158, 262. 456 minus 178, 278. 484 minus 182, 302. And 505 minus 172, that is 333. And finally, the pore pressure parameter A. So this is U divided by sigma 1 minus sigma 3. So 108 minus 130, which is 0.78. Okay, so I think it would be better if we do the sample calculation for the same data. So this is basically okay. Now the pore pressure coefficient for other data is 0.66, 0.57, 0.50, and 0.50. So it's simply your U divided by sigma 1 minus sigma 3. Okay, So now once this uh, data are with us, means q, q prime, p and p prime, then we can plot the stress path in terms of total and effective stresses. So it will start from this 300 value, 300 and 0. So for example, if we consider this one, q and p, so it will start from 300 0, then 369 69. Okay, so 69 and 369. So each unit is basically 10 along both the directions y and x. So it will be 369 something here. Yeah. Then 420 120. So this is your 420 and this is your 120. Next 456 156. 456 and 156. And here 484 184. 484 184. And 505 205. Okay, now if you draw all these points, so it will become the TSP, that is the total okay. So we have already drawn the total stress path. Now I will request you similarly you draw the, so this is a homework. So by utilizing the value q and p, we have drawn the total stress path. Now it's your turn now, so you please draw the effective stress path. Yes. Okay. So this is the homework. It's a very simple. Just you have to first plot the data and then you have to connect those data by a line. Okay. So the qualitative trend. So for example, 261 and 69. So 261. Then put 120 to 62. It's 69 and 260. Okay. So suppose in this fashion, so it will go. And the difference between these two will then give you the pore pressure. So please draw this effective stress path at your home. And if you face any difficulties in drawing this stress path, then please let me know in the upcoming session. Okay. So yeah. So this is all about problem 3. Now we'll take the next problem. Okay, so one more part is still remaining to solve, that is the variation of pore pressure coefficient A during the test. So by utilizing this last row data and the first row data, okay, we can plot this type of variation. This is the variation of A with epsilon A, that is delta L by L0. Okay, so it's a simple task. So just you have to plot these values from the table. Now we'll take the next problem. So this problem is about a consolidated drain traction test, which was carried out on a sand sample with the known effective shear strength parameters, that is C prime is 0 and phi prime 30 degree. In the test, prior to failure, when the sample was undergoing axial compression under constant cell pressure, the drainage valve was accidentally closed, and at failure, 360 kPa deviator stress was recorded along with 70 kPa forward pressure. Now, if the test is repeated without such error and no back pressure is applied in either of the tests, what is the deviatoric stress at failure? Okay. So means two conditions are mentioned in this problem. So though in the first case we were trying to perform the consolidated drain test, but due to some accidental errors or due to some accidents, it has become a consolidated undrained test. So this is the C. Now at present we are trying to actually perform the consolidated drain test and with all kind of precautions, okay, so that there is no such errors repeated. So for CU, so as you know that sigma 1 will be sigma 1 minus U and sigma 3, okay, sigma 1 prime and sigma 3 prime, sigma 3 minus U. Again sigma 1 you can write sigma 3 plus delta minus U. Now sigma 3, that we don't know, okay, that we have to determine from the given data. However, this delta sigma is given as 360 kPa and the U value is given as 70 kPa. So we can substitute here. Okay. So if we substitute, then this value would be 360 and this is minus 7. Sigma 3 plus. Similarly, this will be minus 7. Now we know that C prime is 0 and I prime is 30 degree. So we can use this relationship. The sigma 1 prime is sigma 3 prime tan square 45 degree plus 5 prime by 2 plus 2 C prime tan of 45. Now this C prime, this is 0. So if you substitute the values here, sigma 1 prime, this is your sigma 3 plus 270 minus u equals to sigma 3 minus 17 to tan square 45 plus 35. This will be 3. Sorry, I think I made a mistake here. This is simply so the confining pressure was 250 kPa. Now we'll move on to the present test, that is consolidated drain. Now here the sigma 1 prime would become sigma 1 and sigma 3 prime would become sigma. So sigma 1 prime, this will be again sigma 3 prime and square 45 is 5 by 4. Same C prime is 0 and this value will be 50. So therefore sigma 1 prime would be 250 multiplied by 3. Okay, so 5 prime is 30 degree. This will be 250 divided by 3. That is 750. So therefore the deviating stress would be sigma 1 minus sigma 3. This is 750 that is 5. And this is the answer. So therefore the trick was in determining the confining pressure. Okay, once the confining pressure is known, you can easily calculate the deviating stress at failure for the actual consolidated drain test. Okay, so now we'll take the next problem, and this was related to vane shear test. So a vane 150 mm height and 80 mm diameter was used to determine the undrained shear strength of soft clay strata. Torque applied at failure was 45 Newton meter. Subsequently, the soil gets completely remolded and the remolded soil is sheared at a torque of 17 Newton meter. Calculate the sensitivity of the soil. So we'll start with this sensitivity. What is sensitivity? So sensitivity is defined as the ratio of QU undisturbed to QU removed. Now this QU undisturbed, again you can write it as 2 times CU undisturbed divided by 2 CU removed. 2 cancel out, therefore CU undisturbed by CU. So therefore we have to determine the CU value, unread position value corresponding to each of these two conditions, that is the undisturbed and the remolded, and that will be based on the vein shear test data. Now the vein shear test, as you know, torque is basically applied in the vein rod, and this torque will be resisted by movement the cylindrical surface. So a cylindrical soil mass will basically form at failure, and the movement resisting movement from the surface and resisting movement from two ends, that is top and bottom. Okay, now this MS we can write, because if this is the shear stress distribution at failure, so this is your CU and this is also your CU, this length is your H and this length D. So this will be pi D CU D. Okay. Okay, sorry. So this will be pi dH CU into d by d. And this 2me in general can be represented as beta CU into pi d cube by 4. Now this beta will vary depending on the distribution at the base and top. So at end, if the distribution is triangle, so beta will be half. If it is uniform, beta will be 2/3, and if it is parabolic, then it will be 3/5. Okay, so anyhow we'll proceed with the general expression. So T, this will be pi cu d square h by 2 plus beta dq by 4. Okay, so u will be t by d square h by 2 plus beta dq by. Now, as you can see from this expression, that if d, h, beta, these are constant, because for a when, as it's used for the test, for performing the test, the dimensions are constant. So height is 150 mm and diameter is 80 mm. So your d is 80 mm and height is 120. Again, you can go for any of this distribution. Suppose, for example, we are going for uniform distribution, so beta will be 2/3. So in this fashion, or in this way, gh beta becomes constant. So therefore, if this becomes constant, so as you can see, your cu is proportional to. Okay, so whatever undrained question you will get, that will be linearly varying with the applied torque. If this is the case, then your sensitivity what we have defined earlier as cu undisturbed by cu remolded will now take the form as torque undisturbed by torque remolded. The torque undisturbed was 45, I remolded 17, right, by 17, and it is 2.65. Okay, anyhow you can calculate the undrained coefficient from the applied torque, the dimension of the vein rod, and the beta value, and then you can take a ratio of these two cu values corresponding to the undrained, undisturbed and rewarded case, and you can obtain the sensitivity value. However, for the ease of simplicity, so you can directly take a ratio of these two torque values, that is one is for undisturbed case and another one is for remolded case. Okay, so both will give you the same answer. So any problem till now? If not, then we'll take our last problem. So in this problem, consolidated undrained triaxial test on an over-consolidated clay resulted in the following shear strength parameters. The undrained coefficient value is 15 kPa and the drained coefficient value is 15 kPa and the drained friction angle is 22 degree. The value of Skempton A parameter at failure for in situ conditions is estimated to be minus 0.16. Now for an unconfined compression test, the specimen sheared at a compressive stress of 126 kPa. The initial value of negative pore pressure for the soil is okay. So what we'll do first, we'll first determine the state of stress at failure. Now what are the state of stress at failure? So at failure, your sigma 1 minus sigma 3 is 126 kPa. Again, you know that for unconfined compression test, sigma 3 is 0. This is for unconfined compression test. Okay, so therefore your sigma 1 will be simply okay. So before that, we'll calculate the pore water pressure at failure. So delta U, that you know that AB is basically delta U by sigma 1 minus sigma 3, or and for saturated sample this B will be 1, so it will be A times sigma 1 minus sigma, that is 0.16 times 126. So this is minus 20.6. Now let's say your E0, the initial value is the E0. Pore water pressure initial pore water pressure is 0. So therefore your final will be U0 plus delta U, that is U0 70.56. Okay, so again we know C prime is 15 kPa and phi prime is 22 degree. So you can utilize this expression. Okay, now what are the sigma 1 prime and sigma 3 prime? Sigma 1 prime is sigma 1 minus mu and sigma 3 prime Now what is sigma 1 minus mu? Sigma 1 value is 126. Okay. So since sigma 3 is 0, so sigma 1 is simply 126. So 126 minus u0 minus 20.16. So 126 plus 20.16, that is 146.6 minus 0. 0. Okay. Now if we substitute these values in this equation, so it will be 146.16 minus u0 20.16 minus u0 into 10 of 45 plus 11 square, so 2.2 approximately, plus so this is 44.8. Okay, so 2.20 minus 20, you can write 44.35 plus 54.48 plus 146 point minus 150 minus 57.33. It is 47.8. Okay, so this is the answer. So from the debitory stress, you can calculate the major principal stress since the confinement is 0, confining pressure is 0. Again, from the Skempton pore pressure coefficient, you can Skempton pore pressure parameter A, you can determine the effective stress, the change in change in pore water pressure, and that change if you add to the initial value, so that will be the final one, and that final one if you subtract from the total major principal stress and the total minor principal stress, that will become the effective major and minor principal stresses respectively, and that will follow this equation: sigma 1 prime equals to sigma 3 prime tan square 45 degree plus 5 tan by 2 plus 2c prime tan 45 degree plus 5 tan by 2. So upon substitution, that will give you the initial pore water pressure as 40 minus 47.78. Okay, so with this problem, we'll end our session for today. So this is the homework problem. So in this problem, using a triaxial apparatus, a soil sample was first of all consolidated to an isotopic self pressure of 500 kPa with back pressure maintained at 250 kPa. Then with drains closed, the self pressure was raised to 620 kPa, the resulting in the port pressure increasing to 365 kPa. Following this, the axial load was raised to give an increase in deviated stress of 405 kPa, while the self pressure was held constant. The final pore pressure reading was 456 kPa. The Skempton pore pressure parameter A is. So, first you have to calculate the Skempton pore pressure parameter because Skempton pore pressure parameter B, because the Skempton pore pressure parameter B is defined as delta U3 by delta sigma 3, and then the product of parameters A and B is defined as delta U1 by delta sigma 1 minus delta sigma 3. Now what is delta U3? So this is the change in pore water pressure due to the change in cell pressure. Now as you can see, with drains closed, the cell pressure, if the cell pressure is raised to 620 kPa from 500 kPa, the pore pressure increases to 365 kPa from 250 kPa. So what is the change in pore water pressure? So it's 365 minus 250 due to the change in cell pressure of magnitude 620 minus 500. That means the B value is 0.96. Okay, so this is the first phase. Now in the second phase, your axial load is basically raised by an amount of 405 kPa. Okay, so that means this is the delta sigma 1 minus delta sigma 3. So this is your 405. Now due to that, the change in pore water pressure is 456. This is the final reading, and this is the reading before application of this axial load. So 456 minus 3, 456 minus 365. This is the delta U1. Okay, so this is the change due to the application of this axial load of magnitude 405 kPa. Okay, deviated stress. So 456 minus 365 divided by 405, so this is 0.225. Therefore A, so this will be 0.225 divided by 0.96. So which is 0.23. So it was a very simple problem. Just you have to know the definition of this Skempton pore pressure parameters A and B. So B, this is defined as the ratio of delta U3 to delta sigma 3, where delta U3 is the change in pore water pressure due to the change in confining pressure by delta sigma 3, and the product of A and B is defined as the ratio of delta U1 to delta sigma 1 minus delta sigma 3, where delta U1 is the change in pore water pressure due to the change in deviated stress. Okay, and delta sigma 1 minus delta sigma 3, this is nothing but the deviated stress. So from the first reading that is mentioned in this problem statement, that when the drainage valve is basically closed and the cell pressure is basically increased from 500 kPa to 620 kPa, that means by 120 kPa, the pore pressure is basically increased to 365 kPa, from a value of 250 kPa. So this is the change in excess pore water pressure due to the change in self pressure. Now this ratio will give you the Skempton pore pressure parameter B. Now coming to the second phase of this testing, that now the self pressure is basically kept constant and the axial load is basically increased. Now due to a increase in deviatoric stress of 405 kPa, the pore pressure is basically seen to increase from 365 to 456 kPa. So what was the change, or what is the change in pore pressure? So this is nothing but 456 minus 365, which is denoted by delta U1. And what is the change in deviatoric stress? That is delta sigma 1 minus delta sigma 3. It's 405 kPa. So this ratio will give you the product of Skempton pore pressure parameter A and B. So you know B from the early phase of this testing. So if you divide this product by B, that will give you the Skempton pore pressure parameter A, and which is required to determine for this problem. Okay. So with this, we have come to the end of this session. So we'll again meet on next Sunday, that is on 7th March at 5 p.m. So in between, you will try to solve this problem 3. Okay, so I have basically left one problem for you, so I didn't solve it fully. So the total stress path I have only drawn, and the remaining part is plotting the effective stress path. Okay, so I will request all of you, please try this problem at your home, and if you face any difficulties, please let me know in the upcoming session. So except this, we have solved all the problems which we have selected for today's session, and we mostly considered the construction of stress path, then determination of shear strength parameters by graphical approach, and the determination of Skempton pore pressure coefficients of parameters A and B, and to some extent this determination of initial value of negative pore pressure for an unconfined compression test, where the drain shear strength parameters were given, Skempton A parameter was given, and the deviatoric stress at which the failure is attained, that was also given. Okay, so this is a summary for today's session. Now I will wait for a few minutes. If you have any doubts or if you need any further clarification, you can feel free to ask me. Otherwise, I will stop this session. Okay, so thanks a lot for joining this session, and we'll meet again on next Sunday.